Good evening, everyone. This is Amy Tackett, and I had chosen to discuss showing how the numerical value of the equilibrium constant, or the Kc value, changes when the stoichiometric coefficients are changed or the reaction is reversed. Here we're going to use the example of sulfur dioxide plus oxygen making sulfur trioxide. Now this reversible reaction, we're going to get the initial Kc value using this equilibrium constant equation, which, remember from our equilibrium chapter, is the concentration value of our reactants raised to the power of our coefficient divided by the product of our reactants raised to the power of our coefficients. So I want to go ahead and give some concentration values here in moles to our equation. And these are going to stay the same here. And what I'm going to do is take these values and go ahead and plug them in to get our initial K value. And then we're going to play with the numbers here. So if you look at this is supposed to be a 2. So you've got 16 divided by 2. Our initial Kc value is 8. And so what's going to happen if we decide to go ahead and change these coefficients? We have to keep in mind that we cannot do multiple changes. We can't say this times 3, this times 4, and that would change the entire equation. It would not be in equilibrium. We would have to either take all of them and say multiply them by 2 or divide by 2. Whatever we decide to do to these coefficients, we have to do to all of them. So what I'm going to do here is I'm going to divide them all by 1. I'm going to divide them all by 2. So we're going to have 1 here, 1/2 here, and of course our molar concentrations are going to stay constant. So what we'll have here is 4 to the first, which will stay as 4. And we'll have 1 to the first, which will stay as 1. And then we'll have 2 to the 1/2. When we put this in our calculator, you're going to get around 2.8. So our Kc value did change when we did change the value of our coefficients. So what did happen? So we divided our coefficients by 2. Our Kc value actually became the square root of our original Kc value. So our Kc value went to 2.8, and it ended up being the square root, which is interesting. So what if we decided to multiply our coefficients this time? So now we're going to take these and say double them. We're going to say we got 4 to the 4th divided by 1 to the 4th times 2 to the 2nd. So what we have here is, apologize for the handwriting, 256 divided by 4, which gives us 64. So how does this correlate with 8 here? It appears that 64 is our Kc squared. So we actually took our original coefficient, or original Kc value, and squared it by doubling the coefficient. So it's interesting to watch how these K constants do change as long as we are changing all of these in unison. So what would happen to these stoichiometric coefficients, or I'm sorry, what would happen to the Kc value if we did flip it? So this is the same equation but reversed. So in essence, when we do that, we also have to flip our Kc value equation. So here, we have the same molar value. We're going to have the 4 here. We're going to have the 1 here. And the 2 here. So now we got to plug in all of our values to see with the same coefficients. We're going to put 4 squared on the bottom. We'll have 1 squared, squared, goodness gracious, times 2. So that's going to actually equal 1 over 8. So how does this relate to our initial Kc value? What it actually did was it was inverted. So essentially, what you're doing is taking the reciprocal of the original Kc value, and you were taking the reciprocal whenever you reverse the equation. So I hope that makes sense. It was kind of interesting to kind of play with this to see how these coefficients would react. It's even taking these and timesing them or tripling them, you would get some pretty large numbers, but still keep the original equation in equilibrium. So I hope this helps somebody, and I hope everybody has a good evening. Thank you.